Okay, so in this section, we're going to be talking about section 3.4, which is the equivalent statement section. So if you'll go ahead and print off your note packet and follow along with me. 3.4, again, equivalent statement. This is the symbol. It looks like a fatter double arrow, sort of like the biconditional, with a little fatter look to it, but that's the equivalent statement symbol that we use. Then, just to review, I want to talk to you about the different symbols in the last section. We learned that P and Q, for that to be true in a truth table, they must both be true to equal true. So it takes two T's. That's the only time that one is true. For P or Q, it can be either or. So they can both be true, one of them true either way. So it's most forgiving of our list. I guess the next one's fairly forgiving too, but either one can be true. For the conditional P then Q, it's only false if you have a true that leads to a false. That's like the father that broke his promise. The boy did what he was supposed to do, but then he didn't follow and keep his promise. So when a true leads to a false, that's false. All the other times, you can see on the list, all the other times that's true. Then we have the biconditional. The biconditional double arrow, it must have the same truth value. So a T and a T is true, and also an F and an F is true. It just doesn't allow the lenient parent up here to have a false that leads to true, to go ahead and do what he said he would only do if this happens. So they have to have the same truth value. So those are our rules, same rules. We keep rolling with those and the symbols. And then what we're going to do in this section is really simple. This is the main lesson for 3.4 is you make two truth tables if needed. Now we have some shortcuts, but the fallback method to find out if two symbolic language problems, if they're equivalent statements, is we can make a truth table for each one and then see if their final answers are the same. If they have the same final column answer, then we say, yes, these are equivalent statements. All right, so I'll do some examples with you. The first one in your packet you see is we have P, if P then Q. Is that the same of not P or Q? And we're going to find out later in this section. That's actually one of the rules, one that does come out to always be equivalent. But we're going to show it, say we don't know that now. Sorry, I gave away that answer, but say we don't know that right now. We just make our truth table. So we have these, just a P and a Q involved here, so we just need the four cases. Either they're both true, both P and Q are true, true, false, false, true, false, false. It's the four options. Then we use these rules that I just reviewed, that if P then Q, and you can see above, if P then Q is true except if you have an F to T, that F to T, T to F, that's the one that's not true. That's the broken promise whenever the bargain is kept true on the first if then, and then they don't follow through. So a T to the F, that's the F. Sorry about that, guys. And then it's true all the other times. Hey, just read the notes. Do what it says. In the notes, it tells us that if we're doing if we're doing if P then Q, all of these cases are true. All right? And so that's the rule we're following. We have a P leads to Q, so it should be true all the times except this T to F. All right, now we're going to do this next problem. So it's a separate problem, and we're trying to see if it's equivalent. So we're going to see if they get the same final answers. So the not P, I might need to make myself a note under that. You know, sometimes this one didn't have any real steps to keep, but this one I need to not P. So make the opposite of P, write down, negate all those to their opposite. And then Q, you can either just kind of look over here, but I'm going to write it down to show that other method of just showing all the steps underneath of it. Okay, so we've got a not P and the Q column together, and then we use the OR rule. Remember, OR says it's almost always true except if it's an F and an F. So F and F is F, but any other time with OR, as long as there's one true there, it's true. All right, then we compare our answers. You know, the answer to this is T, F, T, T. And the answer to the first one, we got T, F, T, T. So, voila, they're the same final answers, so we can deem these equivalent statements. That's really all that we have to do on all of these. That is the rule. We make two truth tables and check it out. All right. All right. Next in your notes. we got some more to practice then. So moving on to number 2, I encourage you to pause the video and work number 2 before you come back into it. See if you can get the final answer there, please. All right, but I'm going to take a minute to write these up here on the board for us. I feel like my marker's not bright enough today. Let's see if I can do better. Okay, oh, that's better. Okay. All right, so the next one, we have P and quantity Q or R, sorry. And we want to know, is that, oh, I'm having trouble making that little symbol. Is that equivalent, there we go, to parenthesis P and Q or P and R. All right, so that's a lot going on there on that one. So we just make our table, but notice we have a P, Q, and R. Anytime we got 3 unknowns, that means we're going to make that bigger table with the 8 cases. So I'll print that out here for us to work on. So we got P, Q, and R. We got 3 players, and that's 3 statements that we have to use. They didn't tell us what these statements stand for because it doesn't matter, but if there's 3 statements involved, you got to have the 8 cases. So kind of a pain, I know. 6, 7, 8. Okay, I think I got the 8 columns going there. So they're either all true, 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 false. You'll never have to make this table by memory. This will always be provided, or you can have it on a note. I'll let you know, though. Don't think that I expect you to just memorize these. Although you could probably think about it long enough. It'd be a pain, but you could come up with this. They're just different combinations of the way 3 things can happen. All right, so we get that down. Then we're going to do the 2 problems. The P and Q or R is one of our problems. Get the final answer to that. Then we'll do this other one, P and Q in parentheses, or P and R in parentheses, and see if they have the final same answer. So remember, when we do these, you can just look over here, or you can write it down here as well. I think if there's no not negations in it, I'll just kind of look over here, Q or R. So I'm going to just focus on column Q and R, and using the OR rule, it just takes, and I'll make a column for that, it just takes 1 true. So true and true is true, true and false, and so on. Here's a false, false, and a false, false. That's the answer to that parenthesis. Then you can either just look over here, or I'm going to write down column P here. You know, it's kind of, that's up to you how many steps you want to show, or if you just want to look over here. Your call. Then we're comparing. Our answer will be column P, and then the answer to our parenthesis, this column, and then we use our AND rule. So remember, the AND rule says it takes 2 truths. It's the most strict about it. 2 truths is true. 2 truths is true. True and a false? Nope. So all the rest of the way down. So our answer to this first compound statement, we've got, and I circled it to kind of help you focus. You might use a highlighter. I don't know if you do that. That might help you too, because it kind of just all does run together. Then I'm going to jump over here and do this second problem. I'm trying to decide if these are equivalent. So my final answer will be when I do the OR part. So I'm going to do this parenthesis, which is P and Q. P and Q, I'm going to look over here at column P, column Q. Using my AND rules, it takes 2 truths. So I'm looking through all of these, only whenever it's 2 truths for AND. All right, that's that answer. Then I'm going to do my AND rule with P and R. So now I'm comparing, and this is where it kind of can mess you up. You might want to put something to cover that, but I'm comparing P and R. So P and R, it takes 2 truths, true and a false. True, true, there's a true, true, true and a false, false, true, and so on. So that's the answer to that. Then, lastly, I'm having trouble with my direction here today. Then I'm taking the answer to this parenthesis, the answer to this parenthesis, and I'm using the OR rule. So ultimately, this is a disjunction. The OR is the final question of it. So when I do OR, it just takes 1 true. As long as at least this one is true, it's okay. So true, 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 false, 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 false. That's that answer. So now I need to decide, well, were they the same? So look at the two things you circled. True, 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 false, 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 false. Again, these came out exactly the same answer. So I could make a list if you're kind of making a running list of things you've already kind of checked. This is not a common one maybe that's used, but this one is equivalent. So you might write it on your list and say, hey, I've checked this one out. It works. So if you see it in your homework, it says, are these two statements equivalent? Here's one we've already checked out. And as you go through these, you might keep a running list of things you do know check out for you. All right, so that's that. Now, next concept is some equivalent statements that are kind of general ones that they want you to know of, some common ones that are used. So the next one we call De Morgan's Law. De Morgan's Law says an equivalent statement whenever you have a negation of a parenthesis. Now this may just blow your mind here. You may just think, how can that be? But I promise you it is, and if you make your truth tables, you will find whenever you do the negation, and maybe we should take time to do that as an example. If you need me to, I'll be sure to do that. But we could make a truth table for this and see that it is equivalent to, if I can draw that, we do distribute our negative sign, like you might think from algebra class. We do distribute that negative sign, but when we distribute the negative sign, it flips the and to or vice versa. So kind of a neat rule. It'll be equivalent to not P or not Q. All right, so it flips the conjunction to a disjunction or vice versa. Okay. It works also when we're negating P or Q. So the equivalent, I struggle with that. Hope you guys do better. The equivalent is not P and not Q. So you do distribute the negation like you probably thought you should. You know, negatives in algebra we distribute. But when you do, it flips that to this opposite. All right, so that's De Morgan's Law, that you can distribute the negative but flip the conjunction, disjunction upside down. Another example on the next page, another equivalent, is if you have if P. This is not De Morgan's Law. It does not fall into that. It's just another equivalent thing. If P then Q is equivalent to not P or Q. And it just is. You can, we did this one actually. That was the first problem we did. This is the truth table we made, and we showed these are equivalent. So again, you can kind of keep a running list, but these are three that's specific in the book, examples that shows up in your homework. But there can be others, so you may want to keep your own running list. All right, so activity. Always pause the video when we do an activity and try it on your own.